Today I will discuss about Rolle's theorem. Rolle's theorem related to derivative of function. That is application of derivatives. Rolle's theorem means application of derivatives. Okay, there are Rolle's theorem, Lagrange's mean value theorem. Now, Rolle's theorem means what? Some statement for a function. Okay. Here we are denoting function by fx. If a statement, because there are statement of Rolle theorem. Okay. First of all, we have to understand what is a statement of Rolle's theorem. For a function, suppose if fx is a function, if fx is defined in short, I am describing a statement. If fx defined in closed interval AB such that, means there are some condition for this function. If this condition exists, then we will get some result. That is the statement of the theorem. If fx is defined in closed interval AB such that first condition is fx is continuous. Fx is continuous in or continuous on closed interval. Second is fx is differentiable in open interval. Suppose we are giving some function and some interval, then we are testing if fx is continuous on AB, fx is differentiable in open interval, and third condition is fa equals to fb. That is, for at end point of this interval, the value of function are same. If these conditions are satisfied for the given function fx, which is defined in the interval AB, then if this condition exists, three conditions, then we get a result. What? Then there exists a real number, suppose C belongs to open interval AB such that f dash c equals to 0. This is the statement of Rolle's theorem. That means for a function which is defined in interval closed interval AB, if this function is continuous in closed interval AB, differentiable in open interval AB, and value of the function at the endpoints are equal, these three conditions are satisfied for function, then we can get this result. What is the result? Between A and B, there will be a number C such that at that point derivative of function is equals to 0. This is our result. So this is the statement of Rolle's theorem. Okay. So for generally question are asking for verify Rolle theorem for the given function in the interval. So verifying means first of all we have to show that these three conditions are satisfied and find a value C by using this relation, and we have to find C such that C belongs to AB. Then theorem will be verified. Clear? This is statement of Rolle theorem. Generally, we are asking questions as verify Rolle theorem. Whether Rolle theorem is applicable for this function in this interval or not. So, testing first these three conditions. Okay, this is the statement of Rolle's theorem. Rolle's theorem, what represents Rolle's theorem? Rolle's theorem, geometrical meaning. If we want to understand geometrical meaning of Rolle's theorem, that means what? Suppose this is y-axis, this is x-axis. Clear? Okay, this is origin, this is y-axis, this is x-axis. Then function, we are given function y equals to fx. Okay, interval is what? AB. Suppose here is the point A or here is the point B. Clear? Now, graph of the function between these two since the function is continuous in the interval AB, so we can draw the graph of the function continuously in any way. And f equals to fb, that means value of the function will be same. Suppose this is value of the function at a means a f. This is the point. Similarly, fb, b here means b fb. fb means value of the function. This is fb. This is fb. This is f. At the point this. These two values are same, that is same level, fa or fb at same level, and function may be any type of continuous curve from here to here. Clear? Suppose we are drawing like this graph. Clear? This is the graph of fx. Y equals to fx. Y equals to fx. This is the graph. Clear? Now, since function is continuous, so continually we can draw the graph, and at each point, because differentiable from A to B, so at each point we can draw tangent. Okay, so here we see that here tangent will be like this at this point. Also here tangent will be like this. 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 That is, and also we know that slope of a line parallel to x-axis is 0 and slope is given by derivative. So at this point, that is, here will be some point, also at this point here will be some point, also this point here will be some point, also this point here will be some point. In these 4 points, the slope of this line is equals to 0, or these are the tangents. So at all these points, here, 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 and also here, 4 points, maybe 1 point. Suppose graph is single graph, then there will be tangents whose slope will be 0, that is C1, Here we get C1, C2, C3, C4. Maybe we can get 1 point, at least 1 point exists. That at that point, slope of the tangent at that point is equals to what? 0. F dash C equals to 0. So this is the geometrical representation. Geometrical meaning means of the Rolle's theorem. What is the geometrical meaning of Rolle's theorem? Means if this condition are satisfied, then the slope of the tangent to the curve at a point between AB is equals to 0. There exists a point at which slope of the tangent to the curve is equals to 0. That is the geometrical meaning of the Rolle's theorem. Clear? So we will solve questions for verifying Rolle's theorem. For verifying, first of all, test this point, these 3 points. If these are satisfied for the given function, then we can apply Rolle's theorem. And for verification, find the value of C, which f dash C equals to 0 by taking this, and C, the value of C must be between A and B. Then theorem will be verified. Clear? Here, take question of verify Rolle's theorem for sin x plus cos x. That is, the function is fx equal to sin x plus cos x. And for this function, we have to verify Rolle's theorem in the interval 0 to pi by 2. Clear? So, for verification, first of all, we have to check for 3 conditions of Rolle's theorem. So, here, solution. Given function, given fx equals to what? Sin x plus cos x. Clear? Sin x plus cos x. Interval is 0 to pi by 2. 0 to pi by 2. Interval is 0 to pi by 2. This is interval and this is function. We have to check one by one 3 conditions. First of all, since we know sin x and cos x, both are continuous function in their interval, sin x and cos x, and their domain is complete real number. So here sin x and cos x, since sin x and cos x are continuous functions, and also we know that by the property of continuity of a function, that sum of two continuous function is continuous. That's why sin x plus cos x is also continuous. So we can write, since sin x and cos x are continuous function, and sum of two continuous function is continuous. So fx equals to sin x plus cos x is also continuous in 0 pi by 2 closed interval. Clear? Second, that is first condition satisfied. Now derivative must exist in the open interval 0 to pi by 2. Here we see that derivative of f dash x, derivative of f dash x equals to cos x minus sin x, because derivative of sin x is cos x and cos x is minus sin x. Clear? So derivative of this, which also cos x and sin x exist in the open interval. Very clearly it will also exist. So which will also exist, which will also exist in open interval 0 to pi by 2. We see that this, which will also exist in 0 to pi by 2. That is, fx is differentiable because derivative exists. So differentiable in open interval 0 to pi by 2. Okay. So two conditions are satisfied. And third condition is fa equal to fd, that is f0 and f pi by 2. Also f0 equals to means sin 0 plus cos 0 in place of x 0 is equals to what? Sin 0 0, cos 0 1 equals to 1, and f of pi by 2 sin 90 pi by 2 in place of x pi by 2 cos pi by 2 equals to sin 90 1, sin 90 1, and cos 90 0. So this is equals to 1. Both are exist. Implies what? F of 0 equals to f of pi by 2. So this is third condition. So we get fx is continuous in closed interval 0 to pi by 2, fx is differentiable in 0 to pi by 2 open interval, and also f0 equals to f pi by 2. So we see that all the three conditions of Rolle's theorem are satisfied. So we see that all the three conditions of Rolle's theorem are satisfied. Okay, and all the conditions are satisfied, and we have to find a point C such that f dash C equals to 0 and C must be in between 0 to pi by 2. Then Rolle theorem will be verified. And also f dash c equals to 0 and f dash c equals to 0 implies f dash c means f dash x equals to what? Cos x minus sin x. Cos c minus sin c equals to 0 because f dash c, f dash x cube, f x equals to sin x plus cos x. So f dash x equals to here cos x minus sin x. So f dash c equals to 0 implies cos c minus sin c equals to 0 means cos c equals to sin c, that is what? Sin c upon cos c equals to 1 implies what? Tan c equals to 1, c equals to pi by 4, tan of pi by 4, c equals to pi by 4, and which belongs to what? 0 to pi by 2. We see that the value of c pi by 4 belongs to 0 to pi by 2. That is, and we find a value, we get a value c equals to pi by 4 belongs to 0 to pi by 2. That is, Rolle's theorem is verified. By taking this, thus we get for c equals to pi by 4 belongs to 0 to pi by 2, for this f dash c equals to 0. F dash c equals to 0. Hence, Rolle's theorem is verified. Because according to Rolle's theorem, if the condition is satisfied, then we can get a point c belongs to 0 to pi by 2 such that f dash c equals to 0. So we get a point c pi by 4 belongs to 0 to pi by 2. So that is the verification of Rolle's theorem. Okay, so we have to verify Rolle's theorem for a given function in the interval. Okay, so try to solve this type of questions. In a similar case, take another questions. Verify Rolle's theorem for function fx equal to root 4 minus x square in interval minus 2 to 2. Interval minus 2 to 2. Verify Rolle's theorem. So given function is now we are understanding these questions in short. Okay, so given function fx equals to root of 4 minus x square and interval is minus 2 to 2. For verification of Rolle's theorem, here also we have to test for condition first. What is the first condition? Fx is continuous in the interval minus 2 to plus 2. Clear? So continuity. Here we see that if we take any value from this interval including minus 2 and plus 2, we can get a definite value. We can get a definite value of the function. Since for each value of this interval, fx has a definite and a unique value. So, limit of this function and value of this function for each point of this interval will be equal. So, function will be continuous in the interval. For each x belongs to minus 2 to 2, fx has unique and definite value. Definite value. We can see here the value will be either minus 2, plus 2 or invariant value. Then we can get a definite and unique value. Therefore, limit of function and value of function will be equal for all x belongs to minus 2 to 2. That is, fx is what? Continuous in minus 2 to 2. This is first condition is satisfied. Second is what? Fx is differentiable in this open interval minus 2 to 2. So here derivative, find derivative f dash x. F dash x equals to, derivative of this is equals to what? 1 upon root function. Is root function? So 1 upon 2 of root of 4 minus x square. 4 minus x square. And also derivative of inner part for 0 minus 2x minus 2x. Clear? That is equals to what? 2 to cancel, minus x upon root of 4 minus x square. Clear? Which also exists in open interval. Which also exist in open interval minus 2 to plus 2. Here 2 and minus 2 not including, because minus 2 पे 0, plus 2 पे 0 आ जाएगा denominator. So these are not including, but in between value के लिए this exists, because here will be some definite value, x is also definite value, so definite by definite some value, there will be some value. So this exists for in open interval. So second condition is true, that is fx is differentiable. Fx is differentiable in minus 2 plus 2. And third condition is what? F of minus 2 equals to what? F of minus 2? 4 minus 2 square equals to root 0 equals to 0. Similarly F2 equals to 4 minus 2 square equals to root 0 equals to 0. So shows that F minus 2 equals to F2. The third condition is also satisfied. So all the three conditions of Rolle's theorem are satisfied for the given function in the interval minus 2 to 2. So Rolle's theorem, and also we see that ये पॉइंट इन बिटवीन दिस, कहां से वैल्यू निकालना है? सी को डेरिवेटिव को 0 सपोज करके. क्लियर? सो थ्री कंडीशन सेटिस्फाई हो गया. अब 0 सपोज करके देखो. सो फॉर f dash c equals to 0, that is f dash c means what? Derivative. What will be the derivative? Minus x by root 4 minus x square. Minus x means c by 4 minus c square equals to 0. So here solving it we get c equals to 0. Clear? Here c equals to 0 by solving. F dash c equals to 0. F dash c means minus x by root 4 minus x square. So c in place of x, c minus c upon root 4 minus c square equals to 0. So multiply 0, c equals to 0. C equals to 0 which belongs to minus 2 to 2. Interval के बीच में है 0. Thus, we see that, thus we get C equals to 0 belongs to minus 2 to 2 such that f dash C equals to 0. That is Rolle's theorem verified for the given function. Clear? Okay. Take another question. Verify Rolle's theorem for the function fx equals to e to the power x cos x in the interval minus pi by 2 to pi by 2. Okay. So, let us try understand these questions in very short. So, solution. Given function is what? Given fx equals to e to the power x cos of x, and interval is minus pi by 2 to pi by 2. Clear? Function is this, interval is this. We have to verify for this function Rolle's theorem. First of all, we are testing three conditions. First condition is, here we know that the exponential function or cosine function are continuous in their domain. We know that exponential function and cosine function are continuous in their domain, and we also know that if f1 continuous, f2 continuous, then their product is also continuous in their domain. Clear? Their domain, common domain is what? Whole real number. So continuous function into continuous function. This is also continuous in the interval. So in this interval, this is continuous. So fx equals to, this is continuous in minus pi by 2 to pi by 2. Okay? First condition. Satisfied? Now second condition, derivative. So here, find derivative. What derivative? F dash x equals to product of two function. Okay, derivative of what? E to the power x cos x. Product of two function, e to the power x first function. First function is there. Second function derivative minus sin x plus first function derivative of first function e to the power x. Second function cos x. So this is equals to e to the power x common cos x minus sin x. So this is derivative f dash x. Okay, f dash x equals to what? Fx cos x minus sin x. This is f dash x. This is f dash x. Okay. This value, the value of f dash x is very clearly exist in the interval minus open interval minus pi by 2 to pi by 2, which clearly exist in minus pi by 2 to pi by 2, because minus open interval minus pi by 2 to pi by 2 exist. Its value exist. Value of e to the power x exist, and also cos x exist at in between value, because and also sin x exists. So this value clearly exists in open interval. So implies differentiable. That is, exist means derivative exists. This is fx is differentiable in minus pi by 2 to pi by 2. Third condition, f minus pi by 2 equals to f minus pi by 2 equals to what? E to the power minus pi by 2 in place of x, e to the minus pi by 2, and cos minus pi by 2 equals to what? E to the power minus pi by 2 cos pi by 2. Cos 90 equals to 0. So e to the power minus pi by 2 into 0 equals to 0. And also f pi by 2 e to the power pi by 2 cos pi by 2. This also equals to 0. Pi by 2 into 0 equals to 0. Implies f pi minus pi by 2 equals to f pi by 2. Third condition also satisfied. So three conditions of Rolle's theorem are exist for this function in this interval. Now we have to test finding a point C such that f dash c equals to 0 and c must be equals to be belongs to open interval minus pi by 2 pi by 2. So here we see that also f dash c equals to 0. F dash c means derivative e to the power x means e to the power c, e to the power x means e to the power c cos of c minus sine of c equals to 0. And we know that e to the power c is not equals to 0 for any value of c. So this is not equals to 0. So cos c minus sine c equals to 0, that is tan c equals to 1. साइन उधर लेना है, साइन के नीचे cos लाना है, tan c equals to 0, that is 1. So 10 pi by 4 implies c equals to pi by 4. This belongs to minus interval minus pi by 2 to pi by 2. Okay. Thus we get a value c equal to pi by 4 belongs to this such that f dash c equals to 0. That is Rolle theorem is verified. Okay. Thus Rolle theorem is verified. So this is very simple method for verifying Rolle's theorem. So remember the statement. First of all, test all three conditions. If this condition is satisfied, then you can you find a value of c by taking f dash c equals to 0 and see if c belongs to open interval, then Rolle theorem will be verified. Okay. So do some questions. Okay.
Question 1 of exercise 5.8. Verify Rolle's theorem for the function fx equal to x square plus 2x minus 8 x belongs to minus 4 2. This is the interval. Okay. So here we have to verify Rolle's theorem. So let us solve. We are given function fx x square plus 2x minus 8 x belongs to this. This is the interval. Now we know Rolle's theorem is satisfied when there are three conditions for Rolle's theorem. Function fx is continuous in closed interval ab, fx is differentiable in open interval ab, and f equal to fb. These three conditions are satisfied. If then we can apply Rolle's theorem, and if these three conditions are satisfied, then we get a result. There is some c in the open interval ab such that at that point derivative is equals to 0. So first of all we have to check these three conditions. The first condition, fx equal to this is continuous in closed interval. Okay. Now since we know that polynomial function is always continuous, so here fx equal to this given function is a polynomial, and every polynomial function is continuous for all x belongs to R. So this implies that given function is continuous in the minus 4 2 also in this interval, because every polynomial function is continuous for all values of real number. That's why in this interval is also continuous. This is first condition satisfied. Now condition second, fx equal to this given, this is differentiable in minus 4 to open interval. Okay. Now since fx is a polynomial and every polynomial function is also differentiable for all x belongs to R. Okay. That's why here function fx is differentiable in minus 4 2. We can prove it in other way like this. Suppose here we see that fx equal to x square plus 2x minus 8. So differentiate it. F dash x equal to 2x plus 2. 2x plus 2 exists for all values between minus 4 and 2, which exist in minus 4 and 2. That is the derivative exists, the differentiable. So Hence function is differentiable in the open interval minus 4, 2. So this, the second condition is also hold, satisfied. Now condition third, f equals to fb. Here a means minus 4, b means 2. So here we see that f minus 4, that is in place of x put minus 4. From the function we can get f minus 4 equals to minus 4 square plus 2 into minus 4 minus 8. Means minus 8 minus 16, 16 minus 8 0. That is 16 minus 8 minus 8 equal to 0. And also f2 that 2 square plus 2 into 2 minus 8, 4 4 4 8 8 minus 0. Okay, that is f minus 4 or f2, both are equal, that is f equal to fb. Hence f minus 4 equal to f2. The third condition is also satisfied. Now hence f minus 4 equals to f2. Okay, now we have to find value of c by taking f dash equal to 0, and c must be in between minus 4 and 2 of open interval. Okay, now test. Here f(x) equal to this, so differentiate f dash x equal to this, 2x plus 2 minus 0. Here f dash x equal to 2x plus 2 implies f dash c equals to, in place of x you can put c, f dash c equals to 2c plus 2. Here taking f dash equal to 2, since all three conditions are satisfied, so and also we see that f dash c equals to 0, if we take, then this is equals to 0, 2c plus 2 equals to 0. So from here c equals to what? 2c equals to minus 2, 2c equals to minus 2. Clear? 2c equals to minus 2, that is c equals to minus 1. Minus 1 belongs to minus 4 and 2. Minus 1 belongs to minus 4 and 2, that is there exists c, is c belongs to minus 4, 2. C, in this interval we get the value of c, there is at least one value of c in between minus 4 and 2. By taking f dash c equal to 0, that is for minus 1, f dash c equals to 0. So Rolle theorem satisfied. The Rolle theorem is verified because c belongs to open interval minus 4, 2. Thus Rolle theorem is satisfied. Okay, so this was the first questions for the verification of Rolle's theorem of exercise 5.8. Take question 2 of exercise 5.8. Examine if Rolle's theorem is applicable to the function this or not. Also, can you say something about the converse of Rolle's theorem from this function? These are the three functions. First greatest integer function, second also greatest integer function, but interval is different. 5 9 here, minus 2 2, and here this is x square minus 1 function, interval is 1 2. In this interval, for this function, whether Rolle theorem is applicable or not, we have to check. Okay, so let us solve. First question, f(x) equal to greatest integer function, which gives greatest integer just less than or equals to x. Okay, solution. We know that Rolle's theorem is applicable to the function f ab to r, from f is defined on ab, that is interval, if following three conditions of Rolle's theorem are satisfied. First, function is continuous in the closed interval ab. Function f is differentiable in the open interval ab, and f equals to fb, that is extreme point a and b. The value of the function at that point should be equal. If these three conditions are satisfied, then we can say the function is Rolle's theorem can be applied to this function in this interval. Okay, so let us solve one by one. Question first. Here, first question, f(x) equal to greatest integer function. We know that the greatest integer function f is neither continuous in the closed interval nor differentiable in open interval, because in the closed interval there is an integral point. We know that at integral point function, greatest integer function is not continuous at integral point. 5 to 9 there is some integers, so at that integral point function is not continuous. Also not differentiable in open interval 5 9, because not continuous, then also function. will be not differentiable in open interval 5 and 9 in between there, because there are integers. At that point, that function is not continuous, so not differentiable. Okay, not continuous, not differentiable. Also, we uh, first two conditions are fail. Also, we can get f5 equals to f5, get integer of 5 means 5, f9 equals to 9, that both are equal, both are not equal, so three conditions are not satisfied. The Rolle's theorem is not applicable to the function fx equal to greatest integer function for x belongs to 5 9, because these conditions are not satisfied. Okay. Now take question second. Here is also greatest integer function minus 2 to 2 interval. In between there are integers 1, 0. As a similar fashion, greatest integer function is neither continuous in closed interval minus 2 to 2, because there are integers 0, 1, where function is not continuous, nor differentiable in the open interval 1, 2, 2, because there are integers. We know that at integral point the greatest integer function is not continuous, that's also not differentiable, both conditions are not satisfied. And also f minus 2 equals to and f2 equals to not equal, f2 and f minus 2 will not equal, f2 equals to 2 and f minus 2 equals to minus 2, that's why these are not equal, so three conditions are not satisfied. Hence Rolle's theorem is not applicable to the function fx equal to greatest integer function for the interval x belongs to minus 2 to 2. Okay. Now condition function third, here fx equal to x square minus 1. So here given function fx equal to x square minus 1 for x belongs to 1 2. Okay. And we know that Rolle's theorem is satisfied if three conditions are satisfied. If three conditions are satisfied, then we can apply Rolle's theorem. That's why condition 1, testing condition 1, fx equal to x square minus 1, we are given. Okay, this is polynomial, so fx is a polynomial, and we know that every polynomial function is continuous. That is, function is not is continuous at x belongs to 1 2. That is, function is continuous in the interval 1 2. The first condition is satisfied. And second condition, here fx equal to x square minus 1, for differentiate it. Fx is polynomial. Also, every polynomial function is differentiable. We know that. Therefore, function is differentiable at x belongs to 1 2. Or we can prove it by finding derivative. It's like this. Fx equal to x square minus 1. So differentiate it to x, which exists in 1 2 open interval. Because 1 2, in between 1 2, any value put x, any value can be put for x, so f dash x will exist, so derivative exists in 1 2, that is fx is differentiable in the open interval 1 2, so condition second is also satisfied. Now third condition, here fx equal to this, third condition means f1 and f2, the value of f1 f2 should be equal. Here f1 equals to x, in place of x put 1 square minus plus 1 square minus 1, so sorry, here will be minus sign, so 1 minus 1 equals to 0, and also f2 equals to 2 square minus 1, 2 square minus 1 3, 4 minus 1 equal to 3, so both value are not equal. Both value are not, since f1 equal to not f2 equal 0 and 3 not equal. The third condition of Rolle's theorem is not satisfied. That's why therefore Rolle's theorem is not applicable to the function fx equal to x square minus 1, fx x belongs to 1 2. Okay, so in all the three cases Rolle's theorem cannot be applied. Okay, here two conditions are satisfied, but one condition is not satisfied. That's why Rolle's theorem is not applicable. So this was the solution of question 2 of exercise 5.8. Here in these questions there are integral greatest integer function. We know that greatest integer function is not differentiable at integral points, because in between in the interval there are integers, and where function is not continuous, and also not differentiable. That's why not Rolle's theorem is not applicable to that function, because for the applicability of Rolle's theorem, three conditions must be satisfied. So in these questions, Rolle's theorem is not applicable to all 1, 2 and 3. Okay, so this was the solution of question second of exercise 5.8. Okay.